Thank you. Okay, great. Thank you. So the next speaker in line is Marcel Keller. Dr. Marcel is a researcher at CSIRO. I never learned to pronounce it correctly. That's a 61, a research lab in Australia. And he is a prominent cryptographer. He works on multi-party computation, and he's the maintainer of this framework, MP-SPDZ, that he's going to tell us about today, a framework that I personally have used, Sahar also have used, and it's a framework that enables computation, as he will explain, is widely used among several researchers. So we're very grateful to have Marcel here. Thank you so much. Please go ahead, Marcel.
Thank you, Danielle. So as Danielle said, I'm going to talk about MP-SPDZ, which is sort of my main thing these days, but of course also about machine learning, to give the whole thing a bit of an artificial intelligence touch. So I gather the audience has probably heard of multi-party computation, but let me still sort of like give a brief introduction for completeness. Essentially, with multi-party computation, we want to compute on secret data. That is, we want to run some protocols between a number of parties. They have their secret inputs that they don't really want to give away, but they want to run some computation on their combined data. And instead of giving it all to like a trusted third party, they can run this protocol, and eventually they will arrive at the result, which they then can reveal to individual parties or everybody. And in MPC, we sort of have some central questions that sort of define our protocol. And these are around things like how many parties do we have in the first place, and how many parties do we kind of trust how, and how many parties do we not trust how. So keywords here are, we might have an honest majority, that is like, 2 out of 3 parties that are trusted. We might have a dishonest majority, just like 1 out of 1 parties being trusted. There's also the question, do we trust everybody to follow the protocol, even the parties we don't trust, or is that not even a given? And all these questions give rise to a lot of flavors or security models. And all in all, MP-SPDZ now supports more than 40 of these. And sort of the reason for me to build this thing, or why it makes sense to have all these security models in one piece of software, is essentially that all these protocols, all these security models, all these protocols in all these security models take the same view on the computation, which is this black box view, sometimes also called arithmetic black box. And then essentially means all the values are inside this black box that the parties cannot look inside, but they know that the values are there. And they sort of get a handle to these values, and then they can instruct the black box to add some values or to multiply some values and so on. Of course, there is an input facility for the secret values from individual parties, and there's also output facilities if the parties agree, or enough parties agree, that the value should come out of the black box, then the black box will release this value. And this is sort of the conceptualization on what's happening, and this is sort of the reason why it makes sense to have so many different protocols in one piece of software, because of course then you can reuse a lot of code between the different protocols. Sort of in terms of the structure of the software, I think in the space, MP-SPDZ stands out by sort of defining its own bytecode and then have a compiler for that bytecode. And having worked in the space for quite a while, I remain convinced that this is the right thing of doing it, because that allows optimizing various things in the compiler. And it also sort of goes in hand with that abstraction that I showed earlier, because what happens in MP-SPDZ is that the virtual machines at the bottom, the one where the magic actually happens and where the bytecode is executed, you have only one protocol, or like a set of related protocols that are implemented, I hope, very efficiently. But at the higher level on the compiler, it's the same infrastructure that is shared between all the protocols, and it's the same optimizations or similar optimizations for all the protocols, and it also allows to have all the functionality, be it mathematical functionality or even higher level functionality like machine learning functionality, to basically have the maximum reusability between all these protocols and security flavors. And that's all I wanted to say about MP-SPDZ. So let's now go over to machine learning and how does MPC tie into privacy preserving machine learning. And the way it's it's usually done, I would argue, with sort of MPC or general MPC, is this model of outsourced machine learning. So imagine you have all these parties that have the sensitive data on the left. There's like neat hospitals that have patient data, and they would like to train a machine learning model on their combined patient data, because of course more data means a better model. But there might be reasons why they're not allowed to give it away as such to a trusted third party. So what they can do instead, they can use a number of computing parties that are symbolized on the right, that then run the training between them, and then give the data owner something back, like either the model, or they even keep the model, and the hospitals can use the model in secret for future applications of the model. I should also say that there's a lot more issues here that MPC doesn't cover. Of course, this doesn't per se protect against model inference attacks, or even how much data is revealed with the output. So going on, before I talk about some nice applications, yeah, I would like to mention, for a more general audience, I think cryptographers might be well aware of that, usually we do quantization, or as we call it in cryptography, fixed point representation. That is, we represent fractional numbers as integers. And that is done for the reason that integer addition in multi-party computation is just so much cheaper than floating point addition, that often there is a case to make this worthwhile, as in some sort of a trade-off between efficiency and the correctness of the model. And I will actually sort of throw back to this issue in the applications. Okay, so I want to talk about two applications. The first one is decision trees, which is what I'm working on right now. And decision trees are an interesting kind of machine learning, because they actually explain what's going on. So if you follow down a decision trees, and like at a decision tree means, like, you know, at every node, you look at your sample, and you and you look at a particular value on your sample and you say, is it larger, whatever, is it true or false, or is it larger than some sort of threshold or not? And depending on that, you go down left or right in the tree, and so on and so on. And then you arrive at a leave node, and then a leave node will tell you the result. But because you remember the path, you can look at the tree as a whole and can sort of see the patterns and see the decisions that lead to a certain result, which is, for example, in neural networks, isn't really the case. It is also well known that the decision trees are very suitable for tabular data, which actually is often the case with privacy relevant data. So think of patient data. You have a patient record and you have certain attributes that come with that patient record, like think, some sort of like measurements, blood tests, and so on and so on. As an example, out of many examples on the internet, is the so-called adult income data set, which is an extract from the United States Census. And sort of the task that comes with that is to predict whether someone makes more than $50,000 per year. And when I ran this with my implementation, you get results like, this is most likely true for someone who's under 60 years old, married to a civilian, because somehow they have this distinction, more than 1 year of education, and more than a certain amount in capital gains. And there's actually several hundred of individuals in the training set where this holds true, and all of them make more than $50,000 per year. So I think this serves as an example of how this works and how this is explainable. So onto my implementation. There is a relatively new paper on just on arXiv so far by a few researchers from Japan, Hamada et al. And their algorithm is heavily based on oblivious shuffling. That is sort of, you take an array of secrets in secret sharing inside the black box, and you want to randomly shuffle them in a way that you can actually undo the shuffle. And there's a number of protocols to achieve that. Like Waxman networks are one keyword here, but for certain in certain circumstances, there's also more efficient protocol. And the reason for this, to use this oblivious shuffling, I don't really want to go into technical details, but just like as a very high level talking point, is what I would call the RAM nature of decision trees. Because essentially, if you would have this data structure, like if you would use this data structure in a clear text computation, of course, you would just sort of maintain some sort of index that points you somewhere, and you look at that data and it gives you like a threshold and where to look at. So that's very RAM, or random access memory. And it's well known that random access memory is like very expensive to achieve in MPC. So I think this is like a case where this kind of very neat protocol and very neat use of oblivious shuffle kind of it sort of demonstrates for me the beauty of MPC, of like finding these solutions that aren't entirely like one-to-one translated from clear text computation. Again, not wanting to go too much into details, there is this computation coming up in this algorithm called Gini coefficients, and then sort of requires division of fractional numbers. And that kind of goes back to, we have to carefully choose the quantization parameters depending on the data size to make this computation happen. All right, so onto results. What I found is that on this particular adult income data set, I could essentially achieve the same accuracy as a clear text computation. That is, you go quickly up to 85%, and then a bit more slowly towards 86%, or a so-called F1 score, because the data set is very imbalanced. Of course, there's way more individuals making less than $50,000 in taxable income. So in that situation, the so-called F1 score is actually a better measure. And as we can see there, yeah, a 0.62, 0.66, just to show that it's the same what you will find on the internet. More interestingly, for cryptographers maybe, is the difference between three-party computation and two-party computation. Namely that this can be done in the matter of minutes in three-party computation with a very efficient oblivious shuffling protocol. However, in two-party computation, I have an estimate now for like 7 or 14 hours. So a lot more time. And this can really be tracked down to the cost of oblivious shuffling. So by the way, all these figures are with semi-honest corruption and one-party corrupted. So the difference here is like that the three-party computation is honest majority and the two-party computation is dishonest majority, which makes this big difference.
Marcel, can you hear me well?
Yes.
Okay, just a quick question. Is the 2PC part, is some of this time part of some pre-processing phase that is independent of the inputs? Or all of it is dependent on the inputs?
Well, in the two-party computation, like we use these Waxman networks, which just is simply like a lot of multiplication. So obviously, the bulk of this cost is pre-processing. Yes.
Do you have an estimate on how much is for the online, the part that only depends on the input?
I mean, so basically, kind of like very rough back of the envelope. I would usually quote like 1 to 1,000. So basically, that only like 0.1% of these 7 hours would be the actual online phase.
I see.
And then like the overwhelming majority for these kind of things is the offline phase. So kind of doing the calculation in my head, 7 hours, that's like 420 minutes,
Yes.
taking 1,000 of that, that would come down to a fraction of a minute. Okay, so maybe it's not 1 to 1,000, because that would mean the online phase is like faster than the free PC thing, which I think is not quite the case. But I would say the online phase is probably comparable to the time of the free PC computation. Just sort of, yeah. So we're like somewhere between 1 to 1,000 or 1 to 100.
So if the pre-processing can be somehow outsourced, or if we can ignore it, we're really talking about comparable times then.
Yes. Yeah. Okay. I mean, that's generally, yeah, that's generally like with like two-party computation, because the cost there, it's like, you know, you need to get your in two-party computation, or at least how it's implemented in MP-SPDZ. It's all about the processing, you know, like you need to triples for multiplication, be it binary or arithmetic. You need your adder bits and so on and so on. That's all pre-processing. So like once you get rid of that, like you just run the Beaver protocol, and that in itself is very cheap. That's just as cheap as the, like, you know, the 3PC computation.
Great, thanks.
By and large. Okay, no worries. So if there are no more questions on secure decision tree training from anyone?
There is another question.
Yes, please.
I've got your report includes the communication cost.
Yeah, so this is like, these are back-to-back times, but so this is running like a collocated, yeah, in the previous version of the slide, I mentioned that this is like AWS collocated C9, C5 9x large instances. So they have like very high bandwidth. So this does include communication, but the caveat is this is in a setting where communication is very fast. Okay?
Yes.
Okay, so sort of that concludes the decision tree training part. I think I still have, was it 5-10 minutes?
Yeah.
Something like that. So then we just go straight over to neural networks, and like slightly older work that I've been working on mostly last year, published this year, is neural network training. So there is this famous data set called MNIST, which is like handwritten characters that should be recognized, well, handwritten digits, that is like 0 to 9, that you would like to recognize from like a 28 to 28 grayscale picture. There is this famous deep learning network called LUNET, named after Jan LeCun, who also invented things like convolutional layers. And I have implemented this in MP-SPDZ and run it. And what we see here, there is actually a slight difference between secure and clear text computation in terms of in terms of accuracy. But that allows us to run this in like in terms of like, yeah, minutes to some hour, like 1 hour for 99% accuracy, a couple of hours for a bit more. Like you can see my mouse, like the 99% accuracy here is the testing error 0.01. So that's like reached around 5 epochs, I think. So if you want to go to the end, it's like it's a few hours. Again, these running times are like, you know, in a favorable communication setting and in a favorable security model, which is like 1 semi-honest corruption out of 3 parties. And now, yes, yeah.
Sorry, so here, are you just recording the training time? Or?
Yes, yeah. This is like, this is a training epoch. But I mean, like, you know, training involves a lot of inference in deep learning. So you could sort of like somehow chop it up and get an estimate for like 1 inference out of it. Because 1 training epoch is like basically running inference for like all the samples in your input, and then running the backward propagation, which is like somewhat comparable in terms of cost, like give or take. So basically, like the throughput is like your epoch divided by twice the size of the data set, which is like what is it, 50 or 60,000 pictures? Yes.
Is this 2-party setting?
Come again?
Is this 2-party?
No, this is 3-party. So that's what I meant, like the favorable setting. This is like one. It's like one out of 3 corruption.
In the architecture that you use, is there any activation function in the architecture?
Yes. Yeah. So basically, this is like a lot of like leaving a lot of details because of the time, and I just want to present high-level results. But yes, so basically, like we have implemented softmax like properly. So basically, the architecture is there is like 4. I think there's 4 linear layers. So like 4 layers with parameters. That's like 2 convolutional layers, 2 dense layers, every of these layers has a ReLU activation, or like every one but the last one. And then at the very end, there's a softmax to sort of like determine a probability distribution among the possible outputs. Okay.
Yes.
Okay, so yeah, I only got a couple of slides left. Here is a comparison to some prior work in that space, because obviously I'm not the first one implementing this. Like one particular framework that has made a bit of waves is Crypt10 by Facebook Research. They add MPC functionality to PyTorch. But I think the issue there is they have less accurate approximation of nonlinear function, most notably the exponential that is used for softmax. And the result, you can see that the accuracy is lower than our implementation. And this is really, I would like to emphasize that this is really favorable, because essentially, like, no matter what parameters you choose, it will diverge like sooner or later. So it's like really not suitable to this, I would say, is a classic neural network task. It is also much slower, but that is easily explained by the fact that it's purely implemented in Python. And as I mentioned before, MP-SPDZ, like the actual computation, is in C++. And that almost brings me to my last slide. Here again is sort of an overview over the MNIST training in a number, in quite a range of security models, which sort of demonstrates the versatility of MP-SPDZ. And you can also say that the cost really varies a lot as you increase the number of parties, increase the number of corruptions, and of course going from semi-honest to malicious as well.
One question.
Yes?
Do the results have to be explainable?
Sorry, I didn't catch that.
Are the results explainable?
Are the results explainable? As in the can I give a reason why this is more expensive and this much more expensive than that?
No,
Yeah, if you're asking the yeah.
Oh, you mean explainable in the machine learning sense?
Yes.
Okay. No, well, I'm not an expert on this matter, but kind of my takeaways from hearing experts speaking on this matter, that like with neural network training, this is essentially impossible. I mean, this there's like so many, even MNIST, which is sort of this sort of the hello world of deep learning. There's so many parameters already. I think it's around like a decent fraction of a million or several million. So it's just I would say the short answer is no.
No, I'm not talking from this perspective. I'm talking even if you look at the top features. Have you done a model agnostic analysis of that system?
I didn't quite catch that, but it's just that I have not engaged in the machine learning aspect of this at all. So basically, I have taken what people have done and I've implemented in MP-SPDZ. And I cannot try to match the accuracy results, and that's it essentially. Okay. Yes. So And with that, that's actually already the end of my talk. You can find the software on GitHub. There's about 200 pages worth of documentation on readthedocs.io. There is a paper about MP-SPDZ on IACR ePrint. There is the ICML paper about the deep learning implementation. You can find it on Archive. And last but not least, you can follow me on Twitter. And that's my talk. Thank you very much for your attention.
Thank you so much.
And of course, I'm happy to take questions. If
Perfect.
there are any.
So we have taken some already for the audience. We're wondering if there are questions in Zoom or Huba. Sahar is looking at it right now. No questions. So Marcel, I do have a quick question just to finish. So you mentioned Crypten integrates with PyTorch. I think I'm aware of that. Like I remember you provided some interface, some high-level interface for programmers to implement neural networks and other tools. Is that right? Like if convolutional networks, convolutional layers, and all these different tools. There are tools for that in MP-SPDZ, correct?
Yes. So there is this other framework called like EasyPC, and like for some earlier work, I did sort of like some translational stuff there. There is yeah, and also like at some point I sort of like added sort of like a rough replication of the Keras interface. But so basically in the end, like the issue like sort of like the issue remains is that this all very sort of like punctual, and you can't just kind of copy and paste your Keras or whatever code and like expect it like to run, like partially because the interface isn't really there, and also partially there might be like functionality that simply so like isn't there as such in MP-SPDZ.
And do you expect to add some additional interface, like something that enables seamless integration with, for example, TensorFlow or PyTorch?
I would say not in the short to mid-term, because I think it would take quite some like resources to do that, which I don't really have available. So and it's like it's sort of like hard to say, you know, it's a bit of an uncanny valley there, you know, like I could work like I could work more on making this happen, but it wouldn't still kind of go all the way, which might be even more disappointing maybe. So yeah, so the short answer is like not really. Like I kind of prefer to work like one level lower, like as with this yeah, you know, rather kind of do something entirely new, machine learning like the decision trees, and see what can be done there.
Okay, well, that makes sense. There's one question.
So follow up on under Relu, I presume you're using approximation instead of the activation function, is that correct?
Whether MP-SPDZ uses ReLU for approximate for
Leonard, for example.
If you're using approximations instead of the actual.
well, not for ReLU, because ReLU is just like comparison and selection. I mean, they surely they're yeah. I mean, there are some approximation as like, you know, they're like when you use it on your on your CPU. So like for example, like MP-SPDZ uses an approximation algorithm for division that is essentially the same as for a division in your CPU. The only difference is that like in MP-SPDZ, like to save on cost, I mean, we use fixed point representation or quantization with like, you know, as low parameters as we can. But when you think of like sort of like just sort of a crude polynomial to approximate a nonlinear function, that's not really what we do in MP-SPDZ.
Okay, Marcel, thank you so much. So for the interest of time, we're gonna stop it there. More questions offline, and thank you so much, Marcel, again.
Absolutely. Yeah, no worries.
Logging in from
Yeah,
this time in your time zone, which I know is quite late.
Well, I'm a bit of a night owl, so like midnight is still okay. But
Okay, thank you very much.
I will be logging off soon.
Perfect, thank you.